Good evening, everyone. It's my great pleasure to introduce our speaker today, Professor Anastasia Fialkov, Professor of Astrophysics and Cosmology here at the Institute of Astronomy here in Cambridge. Professor Fialkov first did her PhD in physics at Tel Aviv University, followed by prestigious fellowships from ENS in Paris and the Center for Astrophysics in Harvard, leading up to setting up her own group here in Cambridge. She is a world-leading expert in the cosmic dawn, encompassing the first few billion years in the universe. Her group is also interested in probing and modeling the nature of dark matter in space. Please join me in welcoming Professor Anastasia Fialkov to tell us about 21 cm cosmology, first stars and beyond. Professor Fialkov.
Thank you very much for the warm introduction. I'm thrilled to give a talk here, and I don't know if it's common that people ask questions during the talk. After, okay, but in any case, if you have a question, please remember it to the end. So I'll be talking to you about 21 centimeter cosmology. Does anyone in the audience know what it is?
It's a hydrogen line.
Exactly. Anyone else? So raise of hands. No? Great. So I will introduce this topic. I will try to describe why it's so interesting and topical now, and then I'll dive a bit into physics of it. What can we learn with this line? So it's a hydrogen line, correctly. What's the status of observations today, and what we hope to do with it in the future? So that's what we observe today from our local universe. We have beautiful observations of galaxies, planets, our Milky Way, galaxies far away. So very detailed and informative observations. But as we go back into the cosmic past, so this is a cartoon that describes the evolution of the universe from the very beginning, Big Bang here. I will be talking a bit more about it, but from the formation of the first particles, how they appeared, formation of the first atoms, which happened around here, and then to formation of this massive evolved galaxies. So it's still a puzzle. How did we get there from the very first initial conditions of the universe to the beautiful observations that we have today? And 21 centimeter cosmology is a way to map the whole history of the universe, and I will introduce this topic to you today. So our observations cover this epoch in cosmic history when the universe was just after the Big Bang, so shortly after 380,000 years after the Big Bang. And this picture here, these spots, blue and red spots, they actually represent the snapshot of the universe at that time. There were no stars, no planets, nothing. There were just mild fluctuations or oscillations in the energy density field. So they're represented by the spots, which shows the overdensity in matter. And this overdensity in matter is observed by mapping radiation that arrived to us from those epochs. So really just after the end of the Big Bang, this radiation was released and it traveled through space and time to arrive to us today. And it's observed by many telescopes, specifically this telescope which is called Planck. There is a large presence in Cambridge of people doing analysis and design of Planck. It's now ended, so we already learned as much as we could from Planck. But if you are interested in this science with cosmic microwave background, there is a lot of people in astronomy department and cosmology, theory, physics department, that work on that. So that's at the very beginning of the universe. And today on this right-hand side, we have abundant observations of planets, galaxies, stars, all the way to the beginning of star formation, more or less. So today the universe is 13 billion years old, much older than it was when cosmic microwave background radiation was formed. And with powerful telescopes such as James Webb Space Telescope, we can see all the way back to when the universe was just 300 million years old. So we have some observations covering this era in cosmic history, and they tell the story of how massive galaxies formed and how they evolved, and we call this cosmic web, the formation of large-scale structure, formation of Milky Way and planets today. However, this is not the whole story, and specifically James Webb Space Telescope, due to its limited sensitivity, it's the most powerful telescope we ever had, but even James Webb sees only the tip of the iceberg of population existing at early times. So if I go back here, at this dawn of star formation, James Webb sees only the brightest sources, right? That's reasonable, but there is the sea and ocean underneath these bright sources, so there is a whole abundance of population, small galaxies, small star-forming regions that we cannot see directly. And that's basically the discovery space of 21 centimeter cosmology, to dig deeper underneath the surface and discover what kind of populations of stars, black holes, and galaxies lived in the universe at early times. So in this language, we have this big discovery space shortly after CMB, cosmic microwave background formation, to the onset of these massive galaxies that we have never probed, and that kind of fuels our ignorance in theories. So this plot here is from a scientific review article that shows our ignorance in the masses of the first stars. So at this epoch, at some point, there was a moment when first stars started forming. I'll be talking a bit more about that. But we don't have observations of that epoch, and our theories diverge at the moment. Different numerical simulations or codes predict different outcomes of how massive first stars could have been. And this plot specifically shows the distribution of masses versus stellar masses. So some curves are here centered at the very massive end, and they predict that most stars formed at this epoch here, which we call cosmic dawn, were probably 100 times more massive than our star, up to even a few thousand times more massive, so huge, gigantic stars. Other simulations, like these blue ones, predict that stars could have been smaller, like more similar to our sun, or even smaller. So these are theories. We cannot do these computations better because of the computing costs. They are very environmental, non-friendly, expensive, and we just cannot afford that. And it's not me personally, it's the community. But observations of this era would shed light on this type of information. And surprisingly or not surprisingly, the most abundant element in this epoch, in the whole universe here, is neutral hydrogen or hydrogen atoms. And this is because it's the easiest element to form. It has just one proton, one electron, which were formed during the Big Bang. And it's the most abundant element that we have in nature, right? So the first element in the periodic table. And the abundance of this neutral hydrogen early on in cosmic history will help us to eventually constrain or measure what happens at early times. So this, we call it hyperfine splitting transition, or 21 centimeter transition, or spin flip transition. And that is because the lowest energy level of hydrogen atom is actually split in several because of the interactions between spins, so rotation of proton and electron. So when the atoms are otherwise the same, but the rotations of proton and electron are in the opposite directions, the energy level is slightly lower than when they're in parallel direction, right? Otherwise, atoms are identical. And if an atom spin flips, so a spin of the electron flips, a photon of the 21 centimeter wavelength is produced. And this is a very low energy wavelength, and this in the 1.4 gigahertz range. So this is a technically forbidden transition. It takes 10 to the 15 seconds, if I remember correctly, 10 to the 15 seconds to have a single atom spin flip in a lab. But because the universe is so vast, the volume of the universe is so big, there are many atoms, and the chance that they spin flip and produce this photon is high enough for us to observe it. So we expect all this volume here, the black regions, be fully populated by this hydrogen atoms, and they have chances, all of them, to spin flip and create observable signals. So we are talking about, in the field, about tomographic scan of the universe, because if the atom spin flips here at this point, because the universe expands from here to us, to the observers, this 21 centimeter wavelength will be stretched by cosmic expansion, reaching tens of meters of length, literally. So between a few meters to tens of meters. And so at every particular point in time, there is a unique expansion or stretch factor that these wavelengths would suffer. And so we today observing at specific wavelengths, we probe corresponding epochs. So if we want to observe very early on in the universe, we need to build telescopes capable to detect tens of meters of radio wavelengths. If it's not clear, I'm happy to discuss it further. But that's basically the picture. So by this expansion of the universe, that it allows us to access every patch of the universe separately by observing at different frequencies. And all this volume is filled by neutral hydrogen atoms that will create the signals. We only can observe neutral gas in that way, and if there are star-forming regions formed at early times, they will produce ionizing photons that will ionize neutral hydrogen, creating bubbles of ionized gas that we call reionization. So maybe you heard this term. And eventually today, all this neutral hydrogen is not there because it's so hot and ionized. So we cannot use 21 centimeter today to probe the gas between star-forming regions, but there are pockets of neutral gas in galaxies. So it's a bit different observation to make. So 21 centimeter cosmology will allow us to probe the whole suite of objects existing at early times through the whole cosmic history, because this transition between energy levels can be spontaneous or stimulated, and it's stimulated by stellar light, and it is different depending on the temperature of the gas. So this line is sensitive to what kind of sources of stars and galaxies exist, what kind of X-ray binaries that hit the gas exist, what kind of dark matter distribution is there. So a very long list of properties of the early universe. And using that, we can actually characterize what kind of sources, galaxy stars, black holes, existed through cosmic history at every age in history separately. So if this is the observational frontier that we have with JWST, this 21 centimeter cosmology is pushing it literally to higher and higher redshifts, we call it, earlier cosmic times, by measuring 21 centimeter signal. So there are no confirmed detections yet from this cosmic dawn epochs, but there is a lot of observational effort to try and detect it, because it's very information rich, and it's a probe of the epoch that we have never observed yet. So there are telescopes, including the ones we use in Cambridge. So this one on the top here, it's a kind of tabletop experiment, so it just looks like a table. And it's a radio frequency, low radio frequency telescope that detects an average signal from the sky. So it doesn't point to specific locations, but it sees the whole sky, basically, and just probes the average signal as a function of cosmic time. So this experiment is called REACH, and we have a big group in the physics department that works on it. We are also taking part in these two types of experiments. So these experiments, both of them are composed of many antennas, and that's because they do a Fourier analysis of the sky. So it means seeing the sky in different wavelengths at the same time. And they are called interferometers. So this on the right is called Hera. It's located in South Africa, and it's already active. It provided some interesting upper limits already. I will discuss that a bit later. And this telescope is a new one that is now being built in Australia. And it's, I should have put a picture of Christmas tree here. These antennas really look like Christmas trees. Even in some departments, they put Christmas decorations on them. This telescope is called Square Kilometer Array. It will have a big area coverage, and it is really tuned to detect this epoch of cosmic dawn. Right, I'll skip that. I think I explained that already. So what stars do when they form, so if this yellow thing is neutral hydrogen, neutral gas, each star forming region will carve out bubbles of ionized gas. And so these white things are ionized gas. And that's a nice analogy to imagine what actually reionization is. So we have a Swiss cheese with bubbles. And in the center of each bubble is star-forming region. So white stuff is ionized gas that does not produce 21 centimeter signal, and yellow is the space that will produce 21 centimeter signal because it's neutral gas. So eventually, with cosmic time, most of the yellow will become white, so all universe will become ionized, and that's the end of 21 centimeter cosmology. Some more fun facts. So if we look at the history of the universe from cosmic microwave background formation to today, it turns out that there is a range of epochs that we can observe from the ground. So by putting these telescopes like Square Kilometer Array in Australia, where it's very radio quiet, we say, no noises. And it will inform us about the formation of the early galaxies and the epoch of ionization. So this is the end of the Swiss cheese when everything is ionized. But this era, which we call Dark Ages, when there were no stars yet, is actually inaccessible from ground, and we need to go to space. And this is because the ionosphere, so we have ionosphere, it acts like a mirror for very low frequency radio waves. So if I told you these radio waves will be stretched by cosmic expansion by a large factor, so they will be just bouncing off ionosphere. And the only way to probe this region of cosmic history is to go to space or the moon. This is to give you a bit more overview of types of experiments that we have. So again, both of them are what we call global signal experiments. There is large diversity in designs. People get very creative. So this one is floating on the water for a very good reason, because radio waves, again, if they hit the ground, they would be reflected into a telescope and contaminate the signals, which are very hard to clean. But it turns out that if it's floating on the water, and if the lake or water is deep enough, the radio waves will just penetrate the water and slowly decay, and they will not contaminate the signals that are reflected, so sky signals that much. So these are global telescopes, and there is several interferometers, so similar to SKA and Hera, that are already acting. For example, the big one in Europe is called LOFAR. There is another big one in Australia called MWA, and they both are taking data and providing information already. So this is an example of how real data looks like. We already have data from both Hera, which is this interferometer, and SARAS-3, which is a global signal experiment. We still don't have a detection, as I mentioned, but we have noises that are low enough to start ruling out interesting scenarios in both cases. Actually, there was a detection of 21 centimeter signal. That's how it would look like in reality, published in 2018. And it shocked the community. There was a big kind of excitement because that would, if that's a real detection, it would be really probing the formation of the very first stars here. But there were several problems with this detection. So first of all, it's too strong. So if you look at the normal astrophysical scenarios in gray here, this detection that came from the EDGES telescope is much deeper than what we expect to see. It's very early. It has this squared profile that we cannot easily explain with theories. And it's still a mystery. So this very deep detection can be a signature of dark matter cooling, for example, if gas interacts with dark matter, which is a big question mark what it is, then dark matter can cool the gas and create these deep profiles. But there are no plausible or no well-established dark matter models that could predict that. We need to go to corners of the dark matter parameter space or dark matter theories to fine-tune them to explain this detection. So the team that did this EDGES telescope and conducted the experiment, they're still thinking about it. They haven't retracted their detection, but the rest of the community is very skeptical. And specifically this antenna on the water called SARAS actually tried to rule out the detection. So here we see the noise that rules out, so they don't see the same strong absorption. And a fun fact here is that they actually observed during COVID at a lake that was very near, maybe 100 kilometers away from one of the big cities in India called Bangalore. And during the pandemic, it was so pristine and radio quiet, so there were no noises from, say, cell phones or computers around the lake that they could conduct this very sensitive radio experiment. And now they came back to this lake a few years later, and it's so noisy that they cannot actually see anything. So now they need to go to Himalaya, to very remote locations where they usually go, or Andaman Islands, which are faraway islands in the ocean, to conduct the same quality experiment. So that's how humanity contaminates the skies and in the radio regime, at least. And of course, all the satellites that we have nowadays are also a problem. So for this reason, usually these radio experiments are based in very quiet, radio quiet areas where there is no human presence. For example, in South Africa, there is a radio protected zone where the square kilometer array is being built. In Australia, there is also a radio quiet zone, and in many countries. So square kilometer array is actually being actively rolled out in Australia, and the UK is one of the major financial contributors. It's an international telescope. There are maybe 13 or 12 countries that are contributing to it, and the headquarters are actually in the UK, in Manchester, or Jordal Bank Radio Observatory. The SK is already starting observations, so it will take still 5 years to completely build it. But there are very first observations made with the first antennas on the ground. So you can see our galaxy here and several other active sources, such as M87, Centaurus A, yeah, it's hopefully, fingers crossed. So as I mentioned, we need to go to space to observe this very early times because of the ionosphere, space or moon. And one of the most attractive areas is actually on the dark side of the moon, in a crater that never sees sunlight. There is such a spot there, permanent darkness, and astronomers dreaming to put a radio antenna in there. Unfortunately, it's very popular with industry too, because there's water ice there, and so it's not clear who gets there first and if we'll have a chance to have this pristine sky for science. But there are many telescopes being either planned or already launched or in the stage of design. For example, this telescope DSL has been launched recently. And another experiment here called Astrophysical Lunar Observatory is in a stage of proposal to ESA. And there are many other designs, so different countries, including US, China, India, and us and Europe are creating designs for telescopes on the moon and space. So let's dive a bit more into what can we do scientifically with this line. So I told you that we haven't still observed it, but there is a race to who detects it first. And the reason that people are so interested is that it's really rich in astrophysical information and cosmological information. So it is sensitive to the formation process and distribution and spectra that stars produce, the buildup of galaxies, the nature of dark matter, cosmological properties through this whole range of cosmic histories or cosmic times, the growth of structures in space, how the universe was heated and ionized, what kind of binary stars existed, what kind of dark matter, what kind of black holes existed and how they affected the environment, if there were any radio sources, like our galaxy produces radio photons, but do we expect to see these radio sources at early times or not? What kind of production of chemical elements happened? And so on, so a long list. And if we detect this line over the wide range of cosmic times and spatial scales, we can learn a lot of this. We have very vague understanding of this process now, different theories, but we really need observations to anchor them and tell us what happens. And that's just a nerdy slide where which shows that if we wrongly assume our theory, we will be biased in our understanding of the universe. I again can talk about this more in detail. So what actually we plan to observe? A bit of one equation that gets more and more complicated. So in a very simple way, this is the signal we plan to observe called 21 centimeter brightness temperature. And it basically, we need to propagate the cosmic microwave background radiation through neutral gas, hydrogen gas, to us today. And as the radio photons from CMB propagate, they interact with hydrogen atoms. So if you have a cloud of neutral gas and the photon that goes through, the atoms in the gas can absorb this photon if it resonates with the energy levels. The atom in the gas can also emit photon in the same wavelength and overall distort the amount of photons at every given frequency. So this is called the radiative transfer problem. And to the leading order, we can write it as just, it's proportional to 1 minus the ratio between the temperature, so the temperature of the radio background, divided by the temperature of the gas. Okay, so that means that if we measure 21 centimeter signal, we will have information about how hot or cold the gas is, which is already great. And the theory suggests that at early times, before the formation of the very first sources, the universe was just very cold, dark, neutral, and expanding. And as the universe expanded, if you take a balloon and expand it, the gas inside will cool down, right? It will become colder and colder as the volume expands. So same happens with the universe. The gas in the universe just cools down with the expansion. So it cools down actually faster than radiation, so than the CMB photons. And so if we probe the 21 centimeter here, we would see a signal, we call it absorption profile. So gas will absorb from the CMB. But at some point here, sources such as first binary black holes formed. And what they do, if you have a binary black hole, it attracts the gas, and the gas starts spinning around the black hole. It heats up by that and produces a lot of heating radiation or X-ray photons. And so these X-ray photons can actually heat the gas up, and it eventually becomes very hot. So if we measure 21 centimeter here at this stage, we will see it in what we call emission. So this gas is so hot that it contributes photons to the CMB. So far, hopefully so good, but that's not the end of the story. There are complications. So I mentioned that we only observe neutral gas, and through most of the history of the universe, it actually was neutral. So the gas between star-forming regions was neutral. But then as more and more massive galaxies formed, they started producing ionizing radiation, so carving these bubbles in the Swiss cheese. And eventually, the cheese ended, so there is no neutral gas at all, and the signal disappears, right? So when this, we call it neutral fraction, gets to 0, we cannot observe 21 centimeter signal at all. So this is just measures the amount of gas in the neutral state. But there are more complications, of course, and the coolest, I think, is that actually the signal is sensitive to star formation. So we can measure this contrast only in the presence of stars. And if there were no stars, the background, so 21 centimeter would get to equilibrium with the CMB, cosmic microwave background. So we will measure 0. But what stars do, they just pump this line very actively so that we keep seeing this contrast. And that's not the end. I'm not torturing you anymore, but in reality there are ... that means that the signal is also depends on the cosmology, so how the universe actually propagated, expanded, what kind of structures were there, and also what kind of velocity field, so gas moves around, so that would also affect this line. Right, so very rich in information. And it's also not the end of the story because it's also non-uniform. So first stars, so as I said, the universe here was very dark and cold, and until the stars formed. And what the stars did is that they reheated and reionized the universe. So they produced ionizing radiation, they formed X-ray binaries that created heating photons. But all these photons have some effective horizon, so they cannot heat gas infinitely far away. At some point, they pass all the energy to the gas, and they don't affect gas any further. So we call it effective horizons. It means that every type of radiation can only affect gas around the star-forming region. And so it means that very early on, this distribution of stars, it was very non-uniform, and it created what we call fluctuations in the signal, so it would also be very non-uniform. It's not a smooth function with time. It is like a pattern of peaks and troughs. And that's how a realistic simulation looks like. We call it a light cone. So you see how the gas, this is this 21 centimeter signal, a slice through simulation box, how it evolves with frequency or time, cosmic time. So there is a rich structure of both the intensity shown in color and also the spatial structure that we see if you just look along the y-axis at every frequency. You see, say here, there are these black bubbles. These are ionized bubbles, actually, that we see in simulation. And at these earlier stages, we see heating fluctuations from first X-ray binaries. So what we do in real research is that we create these simulations for given conditions that we assume about the early universe, and then we try to match it to observations of radio signals. So to dive a bit more into details, so I told you about this plot already. It shows us the distribution of masses of stars that we expect to see at early times as a function of stellar mass from different numerical simulations that try to reproduce first star formation. So these are really the very first stars that ever formed in the history of the universe. We call them population 3 stars because today's population 1, that's what people first saw. And as we go deeper and deeper in cosmic past, we encounter population 2 stars that were more chemically poor, And then the very first population of stars, they actually had the pristine chemical composition that was created during Big Bang. So they mostly contained hydrogen and helium initially. So it's still not clear how heavy these first stars were. They might be very light, they might be very heavy. And actually 21 centimeter signal through this dependence on stellar properties can tell us this in the future. So we did quite involved modeling in my group, very bright students who unfortunately left to industry. So we modeled this population 3 stars by following the evolution of star during its lifetime in terms of how bright the star is or how hot it is versus how massive it is. And this diagram shows the dependence for different stellar masses. So we have a dictionary of stellar properties versus their masses, and then we can create, run it through what we call stellar atmospheres code to understand what kind of radiation the stars produce. So given stellar masses, we can understand how bright they are and how their brightness is distributed with frequency. This is called stellar spectra. And depending on the properties of this stellar spectra, we will have different impacts on the 21 centimeter signal. So just to give you an impression of for different distributions of stellar masses, as we see here. So we have one, red one is very heavy stars only in the population, and blue one are mostly dominated by small stars. The combined spectra from a population of stars will be very different. Specifically, if you have a very massive star, 1,000 solar mass star, it will only live for 1 or 2 million years. And it means that if you start forming a population 3 star in the universe, they will burn very fast and there will be no light again. There will be a moment of darkness or millions years of darkness until the population 2 stars can form. In this case, the spectra of a population is very similar to what we have here. There is light, so this magenta shows stellar luminosities. But very soon we have no light and the darkness in the universe reigns again. But if we have a population of very small stars, so like in this top left corner, so they actually are very resilient. They are not so bright, but they last for thousands of million years. So literally. So we have a dimmer population, but of longer-lived stars that shine light on the universe for much longer. So it turns out that these characteristics of how bright stars are and for how long they work affects the predictions for 21 centimeter signal. And it means that in the future, when we have data, we can actually probe how massive the first stars were. So of course, we want to do a more quantitative analysis rather than just hand-wavy predictions. So we looked first at how this affects 21 centimeter signals, and there is some sensitivity, especially in the range of small mass stars. So we see that if a population is entirely composed of these very heavy stars in this range of a few hundred solar masses, we actually cannot use 21 centimeter signal to break populations apart, because they are too similar in their ionizing and heating, ionizing contributions. But if we look at populations, so imagine a population entirely composed of 2 solar mass stars, so entirely composed of 20 solar mass stars, the signals are sufficiently different for us to actually say, this signal is produced by a stellar population that is 20 solar mass stars. So actually, this is only a partial job that we did here. We only accounted for starlight. We didn't look into heating processes. But if we include heating, I can show you what happens next. So I mentioned that 21 centimeters hydrogen signal is sensitive to gas temperature, and especially the contrast between radio background and gas temperature. And it turns out that we need to understand or model properties of heating sources quite well in order to reliably make predictions for the signal. So this is to give you a very simple example. If you have a source that produces very energetic X-ray photons of around few kilo-electron volt, so that's an X-ray energy, these photons can travel far away from sources in neutral universe. So each star-forming region in this case would hit the universe on very large scales and contribute very mild fluctuations in 21 centimeter signal. But if we have very low energy X-ray photons, then they will all be absorbed by the gas right away, and we will see very big fluctuations and on small scales in the temperature maps. The wavelength of X-ray photons depends on their source and the properties of sources. For example, how massive the first black hole binaries are. These are black hole binaries. Should be binary. And other properties. So by observing fluctuations in 21 centimeter, we in principle can go back and interpret what actually is, what kind of sources are there. So we did that in my group by creating a model with, again, metal pristine X-ray binary population. And when we added to our 21 centimeter modeling, we see that so now we have the impact of stars and X-ray binaries, so through starlight and heating. And we see that for different colors here show different predictions for masses of the first stars. We get very different predictions for 21 centimeter signals. So hopefully with square kilometer array, we will be able to identify which one it is and directly constrain masses of this very first population of stars formed before JWST can actually start seeing stars at all. So this is what in principle is possible, but there is already some data that I showed you before. And we have started interpreting it already and learning about the early universe from existing observations. And we do it by running many simulations on supercomputer and then invoking machine learning to create many more models and then comparing them with data. So we use a whole suite of observations. So Hera and Saras I mentioned already, but we also use Chandra X-ray satellite data from radio telescope that observes the big picture radio sky, and also James Webb, which tells us about populations of galaxies existing at cosmic dome. So we do a synergetic analysis where we use everything together. And then we can actually start already now constraining both the interplay of this radio background intensity and how hot the gas is by looking at signals that are constrained by this suite of observations. And I'll stop here and take questions. So I showed you that 21 centimeter is created by hydrogen atoms. It probes the whole history of the universe from very early on after Big Bang to the end of ionization. And it's sensitive to processes such as stellar masses and heating by first supernovae. Sorry, supernovae I didn't mention, but heating by first X-ray binaries. It can probe the masses of the very first stars, and we already have some exciting constraints on this signal from available observations. Well, thank you very much.
Thank you, Professor, for such an engaging talk. So we'll open now to the floor for questions.
First of all, thank you very much for your talk today. I purely enjoyed it. And my question is I'm just curious, what would you expect to happen when all the hydrogen in our universe run out?
Run out?
Yeah.
How do you imagine it running out?
All the neutral hydrogen.
Right, so I got your question, thank you. So what happens, it's a real process that happens. So with the formation of the very massive galaxies, they indeed destroy neutral hydrogen. We call it ionization. So shortly after Big Bang, atoms formed, so proton and electron got together. But if you ionize the gas enough, they break apart and there is no atom anymore. There is just a plasma. And so what happens is that the universe gradually transitions from being neutral as just looking for right here. So at this stage, the universe is neutral and full of neutral hydrogen. But gradually, as we have more galaxies form, they destroy hydrogen atoms. So eventually here, all gas between star-forming regions is actually in the state of plasma. It's ionized and it's hot. This process is gradual and non-uniform. It first happens around massive galaxies, but then slowly galaxies build up. There are more of them. There are more massive galaxies, and also their radiation reaches further. So it's just, there is no hydrogen in the neutral form anymore. It's just ionized, right? But there is still neutral hydrogen in pockets. There are pockets of neutral gas inside galaxies, which we call self-shielded. If they are covered by dense layer, inside this dense layer might be a small portion of neutral atoms still existing today. And they actually observed in our galaxy through 21 centimeter as well.
Do you have any more questions? Okay.
Just show that diagram how far back the James Webb's telescope.
Yeah, James Webb is observing roughly here. So the furthest galaxy from us that I detected is at distance or time roughly 300 million years after Big Bang. So it's roughly here. But again, it's the brightest source at those times. And most of these sources or galaxies that we expect to find are much dimmer.
I'm curious in terms of using simulations, like what is realistic, like what are, like can we learn much about those dark ages through simulation, or there's like too much uncertainty?
There is a lot of uncertainty. I mean, the dark ages are actually less uncertain than this epoch, because here we enter into the regime of star formation, and that is there's a lot of uncertainty. For example, we have a factor of 100,000s of uncertainty in how first heating sources are efficient or not. In dark ages, it's much simpler because there are no stars, no binaries, it just cools down. But there is uncertainty from cosmology. So I mentioned Planck that measured fluctuations from shortly after Big Bang. There are some uncertainties, and they're inherited into that epoch. Plus, there might be uncertainties from the dark matter physics, because there is still a possibility that there are many open theories of dark matter, and then they can create various signatures in this epoch. For example, if dark matter, there are theories where it's warm as opposed to cold, so dark matter particles have some thermal velocities, and what that does is to smooth structures. So we expect to find clumps of dark matter that can form stars later in that case, because they just cannot collapse that early. So I guess the biggest uncertainty is from actually dark matter.
Suppose you have all the telescopes you want in the future and you have observed all that can be observed on the 20 centimeter line and you have analyzed all the data. Will you then be looking for another line like a helium line, or was there no helium in the dark ages, or is there some other spectrum you might be interested in?
That's a great question, and actually people are already looking at it. It's not just me, there is a community. So actually there are other lines, for example, so not in the gas between galaxies, that's mostly hydrogen. Helium is there is very low presence of helium, and also if helium produces a line, it gets absorbed very fast. In case of hydrogen, this line is just very quickly stretches because of cosmic expansion, and then there are no other atomic transitions that can absorb it. That's why it can travel so far. But otherwise, there are lines from galaxies when there is also production of chemical elements, and telescopes such as ALMA in Chile, they detect actually oxygen lines and carbon lines very close to the limit of where JWST also sees galaxy very early in cosmic time. They see abundance of chemical elements already, which is one of the mysteries today, how these galaxies became so big and so, we call them, enriched by chemical elements so soon after the Big Bang. So we do need to probe the whole history to understand how did we get there. Thanks.
When can we expect the answer?
When we can expect
The answer.
the answer? Any day. Well, there is a long list of experiments, as I mentioned here. They're all working really hard to provide the answer. Especially these ones are active now. So this one is in South Africa taking data. This one also is taking data. And it's an incremental progress. So because we have never done this type of science before, it's not like we're doing galaxy observation for 300 years or so with better and better telescopes. But this is something very new. So every time when we progress in terms of getting smaller noises, we hit new types of noises. For example, in LOFAR, which has similar antennas, just like a couple of wires, they found that the crosstalk between each antenna matters when they get rid of contribution of galaxies. So our galaxy is bright, or planes flying above, or micrometeorites hitting the atmosphere create noises. But so we can clean these noises, but then we hit new and new hurdles, such as crosstalk between antennas, or the leakage of polarized sky into the non-polarized section because of how antennae are built. So these are all new challenges that we need to face and then understand how to clean them. So in principle, many of these telescopes have accumulated enough data to already detect the signals, but it's a question if we can clean them well enough to be confident in the detection. And actually, so some people thought that's the answer, but there are still doubts. It hasn't been confirmed by anything. So I would say SK has a timeline of 5 years until they start taking observations, and that is the most promising one.
Okay, in the interest of time, we'll stop here. Let us put our hands together once again to thank Professor Fialkov.
Thank you.
Join us next week at a slightly later time, 7 p.m., for Professor Iwan Burney's talk, head of EMBL. He'll be coming in from London. We'll see you next week.